Okay, the next question concerns skiing down a snowball. Very standard question. It's in your textbook. I'm not sure I signed it. But that kind of question occurs very often on exams and in problem sets. Okay, if you're skiing down a snowball, then as long as you're in contact with the snowball, you're on a circular path. To stay on a circular path, you have to have a centripetal force equal to your mass times v squared over r. Otherwise, you're going to go off the path, and you're going to leave the snowball. Okay. Now, where does centripetal force come from? Well, it comes from the gravitational force. When you're near the top, you have plenty of force toward the center. Now, what do I mean by that? Well, the gravitational force, let's say at this point here, okay? I've got this little segment here where we're sure we have plenty of force toward the center, if this isn't too big of a snowball. Gravitational force is straight down, but the gravitational force can be expressed as a component toward the center and a component perpendicular to that. And the component toward the center is very close to the total gravitational force. So, unless you're moving very, very fast, unless it's a huge snowball, unless you're moving very fast here, you're not going to have a v squared over r that's as great as the acceleration of gravity, and you're probably not going to leave the snowball on this segment. Now, by the time you get down here, well, the direction toward the center has changed. Gravitational force is down here, and it has only a very small component toward the center. So that down here, unless it's a very tiny snowball, one you probably couldn't ski on, at some point before you get here, you're certainly going to need a centripetal force that's greater than the component of gravity in the direction toward the center. And when you get here, of course, there is no component of gravity in the direction toward the center, and you will certainly have left the snowball no matter how slowly you're moving. Okay? So, in this last little segment, we're pretty sure you're going to have left the snowball. So that somewhere between here and here, this is where you're going to leave. You're going to leave at some point, probably in here. Now, again, the point and the angular position at which you'll leave is going to depend on the size of the snowball. We assume that the snowball is frictionless, but that's how we can frame the problem. So the answer I got on this problem from the one person that got it on the test was, well, we're going to leave right here. Well, you will certainly be off the snowball right after you get to this point, no matter how slowly you're moving. But if this is a frictionless snowball, you're going to be increasing velocity, needing more and more centripetal force, and having less and less component of your gravitational force in the direction toward the center. And when those two quantities become equal, that's when you're going to leave the snowball. Now, I didn't ask, but it's kind of an interesting question then. When you leave the snowball, you become a projectile with an initial velocity tangent to the circle and a speed equal to whatever speed you've attained by that point. And it's an interesting question. If the snowball is of the right size, could it be that you leave the snowball, but that your parabolic path after you leave it, because of course once you become a projectile, you follow a parabolic path, could that parabolic path intersect the snowball, and could you possibly leave the snowball, come back and hit it again, and maybe even do that multiple times? So that'd be an interesting question to ponder, try to analyze it.